I'm Lonneke van Bijsterveldt. I work at the Norwegian Meteorological Institute as a software developer, scientific software developer. And I've been asked to give a presentation about this 21-day forecast. Maybe not all of you have actually seen it before, so I thought I'll just quickly show it. It's available for all of the Nordics, so everywhere in Norway, Sweden, Denmark, Finland. You can just, for any location, click at the top at 21-day forecast, 21 dager varsel, and you get a forecast for the next 21 days for temperature and precipitation. I thought in this presentation I would kind of give a bit of an overview of how do we get from all this science that we're doing. Like Thomas, my colleague, showed a lot of research, ongoing research about AI, weather forecasting, and how do we actually get that out into production? How do we get that into a product that actually people use? And to do that, I thought we'd kind of go through two different concepts. One is like the process of how do we implement a new forecast? How do we take users? How do we get users involved in that? And the second one is some of the challenges that we face in implementing this specific forecast and how AI can actually help us with tackling these challenges. So as probably many of you know, IR is a collaboration between the Meteorological Institute and NRK. So NRK is doing all the design, the front end, and we are responsible for the actual forecast of the data. And for this specific product, we also had another collaboration partner, Climate Futures, and they actually kind of initiated the idea, let's have a longer forecast in time. And one thing that is good to mention for IR is that any product that we launch on there, we want to make sure that it's something that's useful for people, that they can actually base decisions on. So we have to make sure that the data that we get out of our models, that we communicate that in a way, that we process it in a way that people can make their daily lives decisions on that. And to make sure that we actually manage to do that, we make sure that users are involved all the way from the start, because they will tell us if the forecast is actually useful or not. So we started up with a target group. We had some farmers within Climate Futures that kind of told us, okay, what are their wishes? What do they kind of need these forecasts for? And examples for that were, for example, when can we harvest our crops? When do we know that the frost is coming? When do we know rain is coming? We kind of like want to have that information to plan further ahead in time. But also decisions like maybe all of you would have to make, when am I going to switch to winter tires, summer tires, stuff like that. So in order to get people for people to actually make those decisions, we wanted to say, okay, we want to show the trend of the weather further in time, but we want to be clear about the uncertainty too that is in the forecast. And so we had to make a decision, okay, for what parameters and for what resolution do we have good enough skill to that people can actually base their decisions on that. And so we initially thought, okay, we'll just give weekly values. We're not going to produce, for example, daily deterministic values like you see here on AccuWeather. They have for the next 6 weeks, they say this is going to be the weather. We can do that, but it won't be very useful. It will just keep changing. It won't be very realistic forecast. And so we settled initially on going for temperature and precipitation because those variables will have a higher scale. We know a lot of people want, for example, wind in there as well, but we just don't think that is good enough scale for people actually based on these decisions on at the moment. And so we produced some variables, and then once we got them out on our API, NRK could start with the first iteration of making a design for that. And so that was the first design, looked like this. So we had pretty quickly already switched to daily temperature values because we realized we can't show a trend over time if you just show weekly values. But we made sure that we kept the uncertainty in there as well. For precipitation, we stuck to weekly values initially because we just don't think there's good enough scale for daily precipitation values, so we stuck to weekly precipitation amounts. Now, with that design, we started doing user tests and user diary studies. So user tests, that is just people, we kind of give people a forecast and we look at how they actually use it. Can they find different things in the forecast? And that is mainly very useful for NRK because they can get an idea if the design works. But what for us on the data side is more important were these user diary studies. We let people use the forecast for several weeks, and we get an idea if they, how they actually use it to make decisions, and if the forecast is of good enough quality, basically. And from those studies, we had a new iteration round, and we realized, okay, just weekly precipitation amounts is not good enough for people. They wanted to actually have some daily values for precipitation as well. Like we said, we're not going to give daily precipitation amounts, but we settled for daily probability of precipitation that we could give sort of with enough certainty in the forecast. So this was the second iteration, and that was actually launched on beta year. That was last July in summer, and so when that was launched, actually people could start using it, and we got a lot of feedback through these feedback forms that people could fill in. And using that feedback, we came to the last iteration round, which is what is launched on the ear now. And so we ended up having a graph for precipitation that is a lot more similar to temperature, so people can compare precipitation and temperature a lot easier. And we still have weekly values here at the top, so we have weekly amounts of precipitation. We have daily probability of precipitation and daily temperature values in the end. Of course, I'm skipping over a whole lot of steps here that we did in the process. One thing, for example, every time we produce new variables or implemented new methods, we do a lot of verification to make sure that the data is the data that we bring out is good enough quality, has enough scale. And of course, the product is not done now. It has good enough quality to be out on ear. People can start using it, and we'll keep using feedback from users to improve the forecast. For example, implementing new artificial intelligence methods to get a higher skill on our forecast. And so the second part is what were sort of some technical challenges that we faced in the development of this project. Of course, there was many. You never foresee everything when you start off. But three I kind of want to highlight, and also kind of see a bit like in what way can artificial intelligence help us to tackle these challenges. So the first one is our model, our forecast at the moment is based on three different input models, three different numerical weather models, and we had to merge those together in a way that it looks like it's one forecast that comes out on ear. You don't want to have any jumps in between the models. The second one is that the 21-day forecast has an overlap of 10 days with the normal forecast that we already have on ear, and we needed to make sure, of course, that that's consistent between the two. We can't have that the first week in a 21-day forecast shows something completely different than in the 10-day forecast. That might seem trivial, but I'll show later why that can be an issue. And the last one is that because this is based on three different input models, it means that when we run our forecast every hour we have to process these three different models. So it is actually quite expensive to run this, and that is one of the reasons why, for example, we're not running it for the whole world yet. We're just running it for the Nordics, because we have to deal with all this data every hour. So a little bit about the data. These are the three input models that we use for this 21-day forecast. So we have maps. So these are all numerical weather prediction models, so all dynamic models. This is no AI models in the input involved yet. So what we have here is maps. Maps is updated every hour, and you see it has quite a high resolution, and we use it for the first 2 to 3 days of the 21-day forecast, and it has 10 ensemble members. Then for up to the first 2 weeks, we used a medium range ensemble model from ECMWF, which has more ensemble members, is a coarser resolution, and it is updated twice per day. And then the last one is the extended range model from ECMWF, which is updated every day and has an even coarser resolution and even more ensemble members, 100 in this case. And so these are the three different models that we use in input. And to combine sort of these three models and get one high resolution output that goes out on ear, that's kind of the process that we call post-processing. So we have our ensemble input models And then we have a chain of different operations that are happening called post-processing, and our output is a 1 kilometer grid forecast that goes out on EAT. And so in post-processing, several things are happening. Like we have to, of course, compute our different variables, so probabilities, uncertainties, so quantiles, and deterministic values. We have to merge the data sets. We have to aggregate from 6-hourly time resolution to daily or weekly time resolution. We have to downscale them because they're all different spatial resolutions, so we have to downscale it all to 1 kilometer. And we have to do some calibration. All these models have their own biases, so we all have to calibrate them separately, so that's a bit of a disadvantage of having 3 different input models. And in this calibration at the moment, there is already some AI involved, and I'll come back to that a little bit later. So to get back to these 3 challenges that I just listed before, the first one is having a seamless forecast, not having any jumps in your forecast because we have 3 different input models. Well, as you can see here, that wasn't very much the case when we started off in the beginning. This is a forecast from June, and that was the reason that we had a big jump. Of course, this could be, an actual change in the weather, but in this case, it was due to merging together different models. And the reason for that is that before the summer, ECMWF only updated their extended weather model twice a week instead of every day. And so that means that here we have the second half of this forecast is based on a model that is 2 to 3 days old, whereas the first part of this forecast is based on models that are, for example, just 1 day old. And then you can get quite a big jump in your forecast, and that we want to avoid. So the good thing is that ECMWF changed their dissemination frequency in July, it was. And so now this is updated every day, so that greatly helps us in making a seamless forecast. Things that we do to make sure that we get as minimum of jumps in the forecast as possible is that we always, whenever the models overlap, we always make sure that we give priority to the most newest, the newest model data that is out. So you always get the most up-to-date forecast. The second issue that we had to deal with was making sure that the 21-day forecast was consistent with the 10-day forecast. And with that I mean, for example, in your 21-day forecast, your daily minimum and maximum temperature should coincide with your 10-day minimum and maximum daily temperature, but also if you have rain symbols in the 10-day forecast, we should also have a high probability of rain in our 21-day forecast. And of course, accumulated values. So if we have our accumulated weekly precipitation, it should add up with the daily precipitations that we have in our 10-day forecast. Now, that may seem quite trivial. Like, why would that actually be an issue? Because they start off with the same input model. They both have a same ensemble input model. And so if we were the only post-processing that we would be doing would be taking, for example, the mean of the ensemble, then they would be the same. We would have the same forecast in both of them. But if you take the mean of an ensemble, you're basically just smoothing out your whole forecast. So you're not really going to get any realistic forecast. Like, this is not something that is a realistic could happen, but not very realistic to always have just a cloud. So what we've done in a 10-day forecast is actually optimize for having a realistic sequence of events. So it is much more likely to have within a day, have some sun, some rain, some clouds. And so the post-processing methods in the 10-day forecast are optimized for that. Then it is already not equal anymore. In addition, in the 21-day forecast, we want to optimize to having realistic weekly accumulated precipitation values. So we use another kind of method for the 21-day forecast. And so this can diverge actually quite a bit. You can get quite different outcomes in your 2 different forecasts. And so yeah, we did a lot of work in trying to make sure that this gets as close as possible together without making either of the 2 forecasts worse. So that was quite a lot of effort has been put into that. Now, where will AI in the future help us out with improving this forecast. So as I already mentioned before, we do a little bit of artificial intelligence already in the calibration method. So right now that is a relatively simple method that works quite well. It is based on something that Thomas also mentioned before, these net atmos stations that people just have in their gardens that measure temperature. And so we use that data to calibrate our forecast from the ensemble input to get to kind of correct for the biases of the model. But that model is only that calibration method is only uses basically temperature as a predictor. So we only use the temperature of observations to correct for temperature. And I think one of the first things that we will implement more AI stuff in the future in the 21-day forecast will be here. So the UNet method that Thomas just mentioned before could be very likely implemented here as well. And then we would use many more predictors. So you would be using, for example, also if it's raining or if there's a lot of wind, that can also affect your temperature. And that will be taken into account then. Another thing, a bit further into the future probably, depending on how the research is going and how well they can implement the higher resolution in the data-driven input models, will be to replace these input models that we have now, which are all physics-based, with an actual data-driven model that Thomas and some other colleagues are working on. And a good thing to realize here is that at the moment, like what has been mentioned before, the AIFS model, it's still just a deterministic model. For this to be implemented in here, it will have to be a ensemble model. So they will have to implement, predicting ensembles, not only a deterministic forecast. And that will, as you can see, greatly help us, because then we don't have to deal with merging different models altogether. We just have one input model. It will greatly simplify things for us. So this is kind of a little bit redundant maybe, but yeah, so like I said, there's two different places where we can implement the AI. So in the post-processing, so replacing more advanced AI methods for the calibration. And the other one is replacing our numerical weather prediction models with these data-driven AIFS model. Up to now, those models are not necessarily better in quality yet. So we'll still need to do these post-processing methods, but it will be a lot quicker to run them in our day-to-day forecast, like every hour, because it just takes a couple of minutes. And because of that speed up, it will help a lot with, we can do reruns for a year a lot easier, which makes the verification a lot easier, and which will help us a lot in implementing new post-processing methods, new variables, because that's one thing that slows us down quite a lot now, is if we have to do verification. That takes a lot of effort and time at the moment with all these 3 different models as input. So I think in the end the quality will also improve, because we can do faster development then. So is AI the holy grail for us? Will it solve all our issues? I think it will solve some issues, like the 3 issues that I had listed in the beginning. It will help a lot with making a seamless forecast, because we could potentially only have one input model instead of all these different ones. It will be a lot faster to run, so we could maybe potentially also run it for larger areas than what we're doing now, not just the Nordics. But some issues will remain, like for example, having this consistency between the different forecast models. Like I said before, you will still have an ensemble input model, and you optimize your deterministic forecast. Yeah, you optimize it for different needs. So your 10-day forecast will have different needs than a 21-day forecast. And therefore that consistency problem is not necessarily solved by using AI. That was it.